Hello everyone and welcome to this channel. If this is your first time here, please subscribe and hit the notification icon so you'll be notified of my new weekly videos on programming for beginners using different modeling applications. In today's video, you will learn how to model simple Toluene Organic Rankine Cycle in Microsoft Excel. I've done simple ORC model in MATLAB for R11 and R245FA working fluid in my previous video. However, for some of my students who don't have access to MATLAB, I decided to do the ORC model in Microsoft Excel, but this time I'll be using Toluene Organic Fluid as a working media. I've provided a link to the R11 and R245FA ORC model with MATLAB below this video. All fluid properties were obtained with CoolProp fluid library. For those of you not familiar with CoolProp, CoolProp is a free open source fluid thermophysical library where you can access hundreds of fluid properties. This is similar to RefProp, but unlike RefProp, CoolProp is free and you can call CoolProp library in Microsoft Excel. If you are interested to know how to set up CoolProp in Microsoft Excel, I've also provided a link of my previous video on CoolProp setup in Microsoft Excel below this video. Let's jump into this quickly. This is the process diagram of a simple organic Rankine cycle, and this is the TS diagram of the Toluene Organic Rankine cycle with Toluene Organic working fluid. So from this diagram, the working fluid temperature leaving the boiler or the evaporator is 550 Kelvin, and it goes into the turbine at a dryness fraction of 1. The pressure at this point has been specified to us here as 2.4729 megapascal. And then at point 2, the fluid is gradually leaving the turbine, and at this point we don't know what the temperature is, so we need to find what temperature at this point is. But however, we know that the condenser temperature is 298 Kelvin. So, and following the constant pressure line, it means that the pressure at this condenser point will be same pressure at point 2. So obviously at point 2, the working fluid is superheated. So we are going to find all the properties of the fluid at point 1, point 2, point 3, point 4, and point 5. Over here, I've shown the description of all the acronym I used in this calculation. So T is for temperature, P is for pressure, S is for entropy, H is for enthalpy, D for density, SV is the specific volume, TW is the turbine work, PW is the pump work, and SOP is the shaft output power, and HI is the heat input, and the cycle efficiency is given as cycle F. And over here, I've provided the relationship for calculating these parameters. So the turbine work is calculated as H1 minus H2, the pump work, H5 minus H4, which is also equivalent to the specific volume, into the pressure at the exit of the pump minus the pressure of the fluid entering the pump. And then for the heat input is H1 minus H5. The shaft output power is TW minus PW. The cycle efficiency is SOP over HI. and the heat rejected is H2 minus H4. Again, looking at this fluid, toluene, its critical point is, its critical temperature is somewhere around this, the tip of this dome shape, which is 591.75 Kelvin. And its critical pressure at this point is 4.126 megapascal. So the temperature and the pressure specification that we have, the working fluid operating in this cycle, is below the critical pressure and the critical temperature. We've also made some assumption here. We've made assumption that the mass flow of the toluene working fluid is 1 kilogram per second. And the turbine efficiency is 92%, which is 0.92. The pump efficiency, we assumed it to be 89%, which is 0.89. So we'll just go through all the knowns to calculate our unknowns. So here we've specified the temperature at point 1 to be 550 Kelvin, and the pressure at point 2 is 2427916 Pascal. All the units I've specified here are the units as can be obtained in CoolProp. So these units are the units specified in CoolProp. So I'm going to be working with this unit. So at point 1, we know our temperature, we know our pressure. So we can calculate our entropy. And again, the fluid properties I've used here, it was obtained using CoolProp fluid property library, which I have provided a link to my previous video on how to install CoolProp fluid property in Microsoft Excel below this video. So I will just go straight to obtain the entropy at point 1. So the entropy at point 1 will be, we'll put the equal sign, and then we use the at, and then we type in proxy, and we use this one here that has proxy. And then we'll enter, because we're looking for the entropy, we use the double invitation comma. So here you have to use the double invitation. If you use single invitation, it's not going to respond, it's not going to work. So you need to use double invitation sign. So I use that because I'm interested in the entropy. And then from this point, I know my temperature, so I could specify the temperature. And that temperature is, so if I select this is B23. You could either enter the value or you use the Excel number. So this is B23 for my temperature. So don't get confused on that. And then the next thing we know there, we know the pressure. So we have to enter the pressure. But before we enter the pressure, we know that at this point, the fluid is in its gas phase. So we need to specify that in the CoolProp string. So all I will do here now is to put in my inverted comma, and I put P, and I specify the string that at that phase the fluid will be gas. And then I select the pressure, which is C23, comma, and then I specify the working fluid, which is toluene. And once you've completed that, you press enter. So next we can find the enthalpy. So we go the same process. I'll just copy this up here. So I wouldn't want to go through typing them all over again. And then I'll paste it here. So we know we are looking for the enthalpy. So we'll change this to H, which is for the enthalpy. We have the same temperature and the same pressure. So we can enter the value now. And this is the enthalpy value. Next, we can find the density at that point. So again, I go through the same process and I paste it here. I change it to D, so the density is represented as D. And we have the same temperature and pressure condition. So I enter. And next, we can find the specific volume if you care to find that. If you're not interested in that, you can leave it, but I'll just put that in here, which is equals 1 over the density. And then next, the Q, which is the quality of the fluid. And at that point, the quality of the fluid is 1. So we can specify that to be 1. So we're through with point 1. Next is point 2, but there are so many unknowns in point 2. Let's start with the knowns at point 2. So at point 2, we know that the entropy at point 1 is equal to the entropy at point 2 because this process is an isentropic process. So we can specify that here, that point 2, the entropy at point 2 is equal to the entropy at point 1. At least that's the known. Then what else do we know? Okay, again, the pressure at point 4, point 3, and point 2 will be the same. But however, we don't know the pressure at the moment at point 4 and point 3, but we only know the temperature. So let's key in the temperature at point 3 and at point 4. So the temperature here is 298 at point 3. The temperature at point 4 is 298. And then we can find the pressure at point 3 and at point 4 as well as point 2. So the pressure at point 3 and point 4 and point 2 will be all the same. So we use the known to the unknown. So what do we know here? We know at point 3 and at point 4, especially at point 4, that the quality of the fluid is 0, which is liquid phase. And at point 3, the quality of the fluid will be 1, which is the gas phase. So we could impose that in CoolProp to obtain the pressure, the constant pressure line. So maybe let's do for point 3. So the point 3, so I could just key in the same thing I have here. But here, rather than that, I will change it because I'm looking for the P. So I'm at point 3. I'm looking for the pressure at point 3. So it's P. I change this to P. And then my temperature, I have to change my temperature to B25. And what else do I know here? Like I said, I know the quality of the fluid because it's at its vapor, dry vapor phase. So it's going to be 1. So I cannot change this. Rather than use P for gas, I cannot change this to Q. Q. And I know that the Q is equal to 1 at dry vapor. So this is 1. And that's it. So we now have the pressure at point 3. We could still go ahead to obtain this, or we can bring this down here because they will be the same pressure, obviously. So I will say P4 is equal to this. And I will also say that P2, which is a constant pressure line, is equal to P3. So we know all our pressures at this point. But what we don't know here is the temperature. So let's go back again now to point 2. We don't know the temperature, but at least we know 2 parameters. So with 2 parameters, we can now find other parameters using CoolProp. First, let's find what the temperature at this point is. So to do that, we need to also know that at this phase, the fluid is superheated. So if it's superheated, it means it's going to be in its gaseous phase and at this pressure. So let's obtain the temperature. Again, I say equals. Now I want to find the temperature at point 2. So I'm looking for the temperature. And what I know is I know the entropy at point 2, which is equivalent to the entropy at point 1. So I know the entropy at point 2. I will select that entropy. So this is D24. Then what else do we know? We know the pressure, that the pressure is C24 and is in its gas phase. So I've made this C24, which is the gas phase, and that's it. So with that, we can click enter, and then it gives me the value of the temperature at point 2. Next, we can find the value of the enthalpy by following the same process. So all I need to do is to copy this and I can paste it here. But here now I'm looking for the enthalpy. So I know my enthalpy, I know my S, I know my pressure. So I could press the enter. So that's the enthalpy. I repeat the same for the density. And that's the density. I do the same for the specific volume. And here the quality of the fluid is superheated. So I could put superheated. And then next we go to point 3. So this is superheated. Next we go to point 3. Point 3 we now know T3, we now know P3. We can find that entropy. Again, we know that at this point the quality of the fluid is 1. So we can use that same property to find entropy at point 3. So I copy this and then I come here and I paste it. So what I'm looking for is the entropy. So I change P to S. And I know my temperature. I know the quality of the fluid. And I can press enter. So this is the entropy at point 3. Then we could repeat same for the enthalpy at point 3. So this should be H. And then we can do the same for the density at point 3. So this will be D for density. And then we can calculate the specific volume at point 3. And the quality of the fluid here is 1. So next we go to point 4. We know the properties at the temperature, we know the pressure, and we also know that the quality of the fluid here is 0. So we could just use the same process. So here becomes paste. So rather than use 25, this will be, we're looking for the entropy. So this will be S, And here, rather than use B25, we're using B26, which is this temperature here. And the quality of the fluid is 0, so we have to change this to be 0. And then you enter. So you see that the entropy at that point is a negative value. So when we look at this TS diagram, we see that the negative value starts occurring from somewhere around here. So it goes negative, so which is in line. Then we find the enthalpy, which will also be a negative value from all indication. So I do the same thing here, and I put enthalpy, and my temperature at this point will be T26, and the quality of the fluid is 0. So that's it. And then I can obtain the density. So I just copy this again and paste it here. To obtain the density, I change this to D. And we now have the density of the fluid. And then we can find the specific volume at 0.4. And what happens here, the quality of the fluid is 0. So next we go to 0.5. What do we know at 0.5? Okay, at least at 0.5, we know that the entropy at 0.5 will be the same as entropy process. So 0.5 will have this is equal to this. What else do we know at 0.5? Okay, we also know that at 0.5, the pressure leaving the pump is equivalent to the pressure going into the turbine, assuming there's no pressure loss. So the pressure leaving the pump at 0.5 is equal to the pressure going into the turbine. So we know the pressure here. So that at 0.5, P5 is equal to P1. At least we know these two parameters. With these two parameters, we can find the temperature at this point. So the temperature at this point becomes, so I'll paste this again. So we use the known to the unknown. So we are looking for the temperature, and we know the entropy, which is the same as the entropy at 0.4. We know the entropy at 0.5. So this will be D27. So this is D27. And then we know the pressure. So we'll have to change this to pressure. And again, we need to determine the phase, because at this phase, it should be liquid phase. So we need to call that string of liquid phase in this CoolProp to identify that property. So I'm going to put liquid. And then I will specify the pressure. So the pressure at that point is C27. Yeah. And that's it. So we'll enter. And you see the temperature at 0.5 is 298.5. Next, we can find the enthalpy. With this known value, we can find the enthalpy at 0.5. So I'll just copy this to save me that process of typing. And then I paste here. Now we are looking for the enthalpy. And we know the entropy, we know the liquid pressure phase. And that's the enthalpy, which is also a negative, which is in line with what we have here. And then we can also look for the density at 0.5. So I'll change this to D. And I go again, enter. And this is the density at this point. and then I can look for the specific volume. And at this point, the fluid is about subcooled. So this is subcooled. So with this, we now know all the points in this TS diagram. So next we calculate the turbine work. So the turbine work will be, from here we specify that the turbine work is H1 minus H2. Okay, we need to include the turbine efficiency. So if we include the turbine efficiency and the mass flow, so it becomes the mass flow. Let's use this as a mass flow, mass flow, and all the components times the turbine efficiency. Let me call it turbine efficiency. And we'll have the same thing here for the pump. So this will be divided by the pump efficiency. So let me call this pump efficiency. So let's implement that here. So the turbine work here becomes, again here we can also include a mass flow. So this will be mass flow times, and here we can now include those parameters here. So this will be equals the mass flow, which is this, times H1, which is this, minus H2, which is this, times the turbine efficiency. If you don't have any turbine efficiency, if it's an ideal process, you can ignore the turbine efficiency. But in this case, we have specified the turbine efficiency to be 0.92. So I will just use that here times, this is B2. And that's our turbine work. Next, we look for the pump work. Again, we follow the same process. This will be the mass flow, which is this, times H5 minus H4. There are two ways you can calculate for the pump work. You could either use the specific volume into the pressure at the exit of the pump, subtracting the pressure while the fluid was entering the pump. So I'll just use the H5 minus H4 to calculate the pump work. H5 minus H4 all divided by the pump efficiency. And that's the pump work. So we can now get the shaft output power, which is the turbine work minus the pump work. And quickly we do the heat input, which is, again, we need to include the mass flow component. So if we include that here, so we're meant to be having something like M times. So if we represent that here, this becomes the mass flow, which is 1 times H1, so which is this, H1 minus H5. And then we can now calculate our cycle efficiency, which is the shaft output power divided by the heat input. Again, I want this to be in percentage, so I'll multiply this by 100 to make it in percentage, times 100. And this is the efficiency of the organic Rankine cycle with toluene, 29.709%. And this is how you can model your organic Rankine cycle with toluene working fluid in Microsoft Excel. I hope you find this video useful and you now know how to model organic Rankine cycle with toluene organic fluid in Microsoft Excel. If this video was helpful to you, please hit the like button and subscribe. Also, hit the notification icon so you'll be notified on my weekly videos on programming for beginners using different modeling applications. And if you have any difficulty doing this model, please leave a comment in the comment section below and I'll be happy to support you in any way that I can. Also, if you have any topic that you want me to cover on modeling, especially with Microsoft Excel, please leave a comment in the comment section below. Thank you for watching and see you in my next video. Bye for now.